Welcome. Hello. This is the second part of the video seminar, which is talking about executable binaries, and this week we're going to look at linking and loading of executable binaries. Firstly, we're going to look at how it's done in general, and particularly on the Pentium, and then we'll look at how it works on the Olimex board and look in a lot more detail at disassembling the code and using some of the tools, particularly the linker. Okay, so if we go on to our system here, and if we start first with the Pentium, if we look at our rather pointless test.c, so it's got one include for standard input and output, studio, standard I/O. It's got main, it's got one variable which is set to 10, and it just prints hello world. Now I'm going to build that, and we're going to put it into an output file called testy.bin. In fact, we don't really need that, but we've got to do that. We're building it statically. The reason I'm doing that is because it will provide slightly more interesting output and is closer to what we're doing on our system. However, this isn't the default. Normally on the Linux system it would build dynamically. The -W lowercase l command is passing from GCC to the linker, hence the L, the following command, ---- for both. It's stopping the compiler doing that and saying, just pass that on to the linker. And what that's going to do is that's going to show us how the linker decides where to put the code, where to put the data, where to put the initialized data, and also any other library files and startup files that it requires. And I'm piping the output into more in order to, because it will just scroll by so that we can see it. We could theoretically have done GCC -c, test.c, and then done LD -static ---- for both, test.o. Because we could call them separately. However, GCC will, by default, if it's being asked to generate an output file, call the linker. So what happens here? Okay, so first it tells us which linker it's using, and it's the GLD, the GNU Linker bin utils. There is another one called Gold that I don't really use. That's mainly because it's for larger systems, which is apparently faster. But we really need to use the GLD, and that's the standard bin utils linker, and it's to version 2.26.1. And these things can be important. It then tells us what code it can generate, and the first one is the one that we're using, which is 64-bit Pentium code. And it said that it's using an internal linker script, and then it's giving us various sort of copyright information saying where it's come from, and the output format is going to be 64-bit Pentium, and the architecture is a Pentium, and the entry point is going to be a label called _start. Things with underscores tend to be significant, and I'll explain a bit more about that later on. And then it says when you're looking for bits of code, which I refer to, which aren't in the object files that the user, the test.c basically, me, that I generated, look in these places. And there's a whole set of different search directories. And that can be varied, but this is the standard one. We use a local lib, so on and so forth. And then finally looking in /lib and things like that. This bit here is sections, is referring to the code sections. And if we go back to our slide, 1 second here, and look, the sections that we're going to be looking at is going to be text, data, BSS. Heap is something slightly different later on, and stack is generated by the linker script. Heap can be allocated by the linker script, but is generally dealt with by routines supplied by the language and the libraries. And if we go back, so the sections here we're providing are going to be the various code, data and uninitialized data segments, and this is the text segment, and it's giving some addresses here and saying I want you to start here, and it's saying this is where execution is going to start from, and then it's got various bits of code which it's going to put in order. And lots of this is system stuff. So you'll note some of it's called GNU build by SLD, clearly something to do with the linker. And the provide instructions are just checks to see if the code's going to fit. And keep means this must be in this order, it must be put in these places. So anything called .init has to go here. Okay, and this then sets up all the various text areas and then the data areas, and it's also got various things like constructors and destructors, which use things like bits of code, which is the C runtime begin, which is the code which is provided by the compiler in order to start the system up. Okay, and that normally works in collaboration with the operating system. So here we can see the data areas and then the BSS areas. Okay, and then once it's done all that, there's also loads of debugging information. Lots of it, which somebody understands, probably, but not me. And then it gives all of the files and where it gets them from. Okay, and most of them are coming from userlib, GCC, the Pentium Linux stuff, and things like libc start. There'll be CRT, will be there somewhere, the C runtime. Things like malloc for memory allocation, and other routines. And some of that will depend on what I'm doing. Mine's only doing print, so it's got standard input and output and a few string copying routines and various support code. Okay, and there's quite a bit there. I mean, there's a lot of code there. And this can be really, really useful for you to understand if you're starting to have problems with your code. However, it really talks to Linux, and Linux does most of the heavy lifting, and also the Pentium itself has got a memory management unit, so this system doesn't really need to worry about that. It just says, you know, I've got 64 bits and here's some code, you figure out where it goes. Now, on the Olimex board, it's a bit different really, because we don't have 64 bits, we've got 32 bits, and in fact, our memory map is a lot more constrained. So we have to be a lot more careful and cautious about this. And as we don't have a memory management unit, we have to do all the memory allocation ourselves. And if we go and have a look at the actual memory map, we've seen this before, this is the same for all of the Cortex M3 series, and the important areas is flash memory and SRAM. So what starts at 8 and 6 zeros, or 2 and 7 zeros, so SRAM and flash. Now, as we also saw last week, depending on the pin settings for boot 1 and boot 0, depends on what's reflected into that memory address. And we're always reflecting flash. So when we've written into flash, it actually appears at address 0, which is of course significant to the CPU. Okay, and oops, let me just go back to VMware. Now, if we look at our program, and I'll just disassemble demo.elf, we'll see that, yes, it does start at the beginning of Flash, and it's got this G underscore, probably global, and vectors, so some sort of vector table. And you'll notice that this address here looks strangely familiar. It's lots of zeros, and we'll find out how it's figured these addresses out. Now, the code itself comes later on. That's just one big table right at the beginning. You'll notice the dot dot dots mean that it's not disassembled zeros. Basically, it's nothing there, and it's not bothered to show us. And then we've got code, and the code goes on and on and on, and eventually we'll get to main, and there's our main routine, which doesn't do a great deal. It branches off to set up the clocks, branches to set up the GPIO routine after it's initialized various parts of it, and then writes to the LED, and probably we could work out which one it's doing by looking at those numbers, although probably a lot more sensible just to look in the source code. However, right at the end is assert failed, which, if you remember, comes right at the end of our main.c, and that's a routine that's called in extremis. Okay, but if everything goes wrong, you call this, and it just loops forever. And that actually stops there. And then there appears in Flash some more code, but it isn't code. This is actually data. Okay, and it's just dumped it in there. It tries to disassemble it and comes up with various things and says things are unpredictable because it's not entirely sure what the hell's going on there. But that isn't in fact, that is in fact the data stored as a big wodge at the end of the program. And that's very useful for the system to do that. Now, how does it know this? Obviously, whoever did this knew the memory map of the cortex, so they were able to do this. But how did this come about? Well, if we remove demo.elf and remake the program, we'll notice that it has all of the .o files, main and startup and so on and so forth. There's the output file demo.elf, various flags, static, and telling us what CPU we're using and the instruction size. We're building statically. We're not using any standard libraries. We're doing it all ourselves. And then there's this -t option. And the -t option is the important one for what we're discussing. And if we type in man ld, type in -t, we then find that it starts talking about the default linker script or the one specified by using -t. And if we skip down a little bit, and here it says -T script file or -- script equals script file. The -- are always the newer options, and they're more verbose and they're more easy to understand. -- script, fairly clear. -t could be anything. However, because of my age, really, I suppose, I tend to use the older format. And this uses this script file as a linker script. Okay. Now we've seen already the default script that was used in the GCC for Linux Pentium. Now the R-none will have a default linker script. They have to, because if there isn't a script given, it will then just put it in some format, and probably in some sort of generic vanilla format that would work on hopefully most ARMs, but pretty unlikely to, really. Because when you're doing this sort of work, you have to specify everything. Now if we look, our script is called stm32f100.ld, and if we do ls, here it is. It's actually in our directory here. And this is the linker script. And it's for our family of processors. So it's the F10X. So ours is the F107. There's the F105, the F103. There's a number of different F100, different families. And these two values here, 256K and 64K, refer to the flash memory and RAM. Okay, this is just a comment. So That's just a convention that's done that. And this has been modified by me from these ones, which I found online. And it's quite common to not write everything yourself. It is also quite common for people to pick them up and not modify them. So, for example, I have seen ones where the flash size has been given as things like 128 when it's in fact 256, which means basically that you're wasting half of your memory. And if you don't know this, or if you've not bothered to read the script, then you'll just waste your memory, which could, of course, be a bit of a security hazard because people could hide code there. So you'd have to be very careful with that. This linker script is quite an important piece of information. Okay, and it will allow you to generate errors. So it says there will be errors if there's not enough memory available. And it says RAM, but actually it could also be flash. It could check on flash as well. It starts here with setting up a variable called underscore minimum stack size. Okay, the underscore is important, and underscores are a little bit like dots in front of file names. They imply that they're significant and something to do with the system. So like dot bash rc, and underscore means that it's a system variable. And the more underscores you have, generally, the more deep in the system it's hidden. And the standard tools won't show these. So generally, most users wouldn't see them, wouldn't know they're around. They don't need to know this stuff, but we do. And we're setting the minimum stack size to 256. Now, the stack, as we know, is used by the processor to handle various variables, and the language on top will probably use it to store local variables and things like that, and pass parameters, and the stack size is important. Make it too small and the program may well crash because it will run out of stack very quickly. How it detects that is an interesting question and problem, but we'll talk about that a bit later. Make it too large, and particularly on a machine with a very small amount of RAM, and you'll run out of RAM space, so you won't have any place to put your other data. So it's a careful problem. Okay. Now, this program is script is going to do a number of things. One of the things it does, we saw in the previous one for the Pentium, it said entry was underscore start. Our entry is called reset handler. And we've seen this name before, and we'll look again a little bit there. But that means where we're starting the code from. Okay? If you don't give that, it will normally just try and guess where the code starts from, and it might get it wrong. This is now defining what memory there is on the board. So it's saying we've got some RAM, it's 64K, it starts at this address, it's read, write and executable, so we can execute code from it, we can read it from it, we can write to it. Flash is 256K, it starts here, and obviously these addresses are gleaned from the data sheets and the various manuals for the processors and boards that we've got. Things like the length of the RAM and flash will also depend on the board manufacturer. If they've put less in or more in, then you'll have less or more, obviously, so you need to check those. Flash itself is only readable and executable, so you can run code from it or you can read from it. And it says you can't write to it. Well, yes you can, but in general what it's saying is that when the program's running, you're not writing to flash, which is generally true. And we write flash using the flash write command on OpenOCD, which is using JTAG. You could have within your program something which did that. OpenOCD is just a program, so you could implement it, but very unlikely. Okay. Now, it sets up again some variables. These have got underscores at the beginning and end, so they're really quite important. And these are setting up various addresses for RAM. So the start of RAM, the length of it, figuring out how big it is, and plonking the stack, underscore stack, at RAM end. Once it's done that, it then does these provide, and you'll see these later on, it checks to see that the stack size is not going to run off the end of memory, so we haven't over allocated. Say for instance we said, oh, I want 68k of stack, then it will just say, I can't do that, I don't have enough memory. Okay, so that can stop and terminate and tell you things aren't going to work. Now, this bit here is dealing, the sections bit is very important, and we saw that in the Pentium one. And just quickly to go to our previewer and quickly do full screen. So these are the things we're setting up. The text, the program code, the initialized data, and the uninitialized data, or BSS, block store segment, I think that's normally called, although I have heard other versions of that. The stack has been set up by the link description script, okay? So that's actually decided where it is and how big that is. But how you stop it growing down is a runtime issue, because obviously the stack can just keep growing. And just because you're set in the link script it's 256, if it grows over that, unless there's some code there to actually stop it, it will start to overrun. And if there's a heap, it can overrun the heap. If there isn't a heap, it might overrun block store segment, which would be a disaster. And the biggest disaster would be that it didn't crash the program, in that it actually carried on running and started giving random values, and that would be a real problem. Okay, so you have to be very careful with that, and we won't see that today, but when we look at NewLib, we'll start to see how these things are dealt with, and they are problems. Okay, and we'll go back to Linux. And so here's the code section, and it's putting that code section into Flash, and it knows what the Flash addresses are. And this bit here, keep, is saying this must go here. Anything else can go more or less in any order, although it's got some order about it. But this is saying anything that's got ISR, interrupt service routine vectors, is startup code and must go at the beginning. Then after that it's code, whatever other code, read-only data. We've seen already that that's actually at the end of the text anyhow. And then there's all this stuff, glue and veneer. This is really compiler stuff to make the whole thing, hold it thing together, hence the name glue. I'm assuming that 7 and 17 means that this is to do with ARM 7 processor and T being 3. I'm guessing. Who knows, really. Then there's lots of tables and linker information. And some of this is to do with things like C++, which requires all sorts of bits of code to be in particular places. We generally don't need to know much about this. And like I say, this all goes into Flash. And then we get the section data, which goes into RAM. And you'll notice it says the start of data. So it puts it here and it gets that address, which is the start of RAM. So 2 and 7 zeros. It does a lot of aligning, you'll notice, align by 4, because it wants everything to end on a divisible by 4 address. And this is in case, particularly in data, if it comes to a non-number, you won't want to use that. It's not very efficient and quite often not possible for the processor to do that, so it continually aligns. And that can cause a small amount of data loss, but it's better than it crashing. And then it puts anything with data into the program, and it keeps variables saying where I'm starting, because it may have been aligned, and where I'm ending, and plonks it in RAM. It does exactly the same with BSS, the uninitialized data segment, puts it in RAM, and then keeps various variables saying where it starts and where it ends. And then you'll notice it does a load of provides. And these provides are just checking that we're not overrunning memory, so that we've actually got enough space here to do what it is that we want to do. And if the program is too big, or if the link description script has got too large a demand for a stack, then it will just stop. Okay. Then at the end there's loads of debug information. This is library information. We're not using any of these libraries. That's the standard C library, that's the maths library, and that's the compiler library. And we're in fact using none of those, so this won't have any impact. And there is lots of this stuff for stabs, single table information, and things called dwarf, which are to do with GNU and debugging, which again you won't really need to know about. Okay, now what we now need to look at is look again at our startup code, and we will see there's reset handler, which is our entry point. So this is going to be the entry point for the code. In fact, the entry command doesn't really have as much impact as you might imagine. What does have more impact is the architecture of the CPU. You'll notice here that it picks up the eStack variable. It actually pretends that it's a function to make it type check it. I'm not entirely sure I understand that, but there you go. You can see now that we've picked up these variables which tell us the start of initialized data, the start and end of uninitialized data, and the start of initialized data at the end of RAM. So that'd be at the end of flash. So that'll be after the text. That will be where it is. And in fact, that bit of memory is sort of lost, but you probably could recover it somehow, but it's not worth it. And then, as we've seen before, we go through and we initialize the initialized data, and we zero the uninitialized data, and then go off and execute our code. Now, the other thing that we can find here, and this table is the vector table, and all of these entries are defined by the Cortex-M3, okay, and by ARM and STMicro. So you've got to have them in this order. You can't, if you want to handle a real-time clock interrupt, then that's where you've got to put it, okay? Because that's where it will go and expect it. And the same for all the other devices like the UARTs and timers, so on and so forth. The other thing about this table, actually, as I realised later on, is that it's not even for our CPU. Because if you look in there, our CPUs, our board, and the ARM 107, the STM F107, has USB and Ethernet, and they're not all mentioned in this. So this is in fact from another member of the Cortex ST10X family, which is not the same as ours. However, it works with ours because we're not using anything that's very specific to our board at the moment, so we don't notice. But later on, if we started using USB and Ethernet, this linker table would be hopeless. Okay, now this says this section is called ISR vector, and as we noted, that gets put into kept as the first bit of code. It's the first bit of code that's put in memory, and it must be done, so the linker will make sure that that goes first. And it's got these global vector table, pointers to functions, so vectors. And the first one is eStack, which, as we remember, is 256 bytes from the end of, no, it's not, it's the end of RAM, and it theoretically goes 256 bytes down into memory, and then reset handler, which is our entry point, okay? And then again, and you'll notice, actually, it doesn't mention our device, which is, these are the value line, STM things. Ours is actually a CL connectivity line. But anyhow, it works. Now, if we look and dump the program, we now see this is our vectors. The link has done its job and it's put the vector table in the beginning, and that address is the end of RAM. Okay, so that's our stack pointer, and that address there is the address of reset handler. Now, this is set up by ARM in the Cortex M3 description that it expects two things in memory. Okay, at the beginning of the memory in 0, and as we remember, 8 6 zeros is reflected into 0 memory, so it's in the right place. The first thing is a stack pointer, the second thing is the address of the entry routine, what we've called reset handler. And all of the rest of the routines are pointing to the default handler, okay? And if we go down, you'll notice there's reset handler and there's default handler. Now you'll probably notice that the addresses are wrong. So if we go back and have a look, it says 16D and 159, and in fact it's 16C and 158. And as far as I can understand, although I haven't read this, but when it looks in that table, it sees some addresses, but it doesn't know if those addresses are to thumb instructions or to 32-bit ARM instructions, or even later model 64-bit ARM instructions. So it doesn't really know. However, we're using thumb, so they're going to be 16-bit, so the address of reset handler is going to be a 16-bit thumb instruction. And what I think is happening here is if it sees an odd number, it knows that it's 16 bits, so it takes one off. If it were 16C, it would then say it's 32 bits and it would just accept it as an instruction. Of course, if you got the instructions wrong by one bit, you'd be really in trouble. So that's how it finds that. And then it goes off and executes the code and eventually executes main, which, as we saw, does those various bits. And this stuff after the end of assert will now be, after reset handlers run, will be moved into flash, so into RAM, sorry, into SRAM. So it will then be, because otherwise, if that was a variable, we wouldn't be able to write to it because it's in flash, okay? But if it's in RAM, we can write to it and we can use it. Okay, so this explains how compilers and linkers work together along with information from the data sheets in order to access, to use the resources and to build executable programs. Just quickly look at some of the other features, so particularly things like object dump. You can look at the symbol table and this will show you all of the various routines. So there we are, the address of data, the start of a text and the start of BSS. So in fact that means there are 28 bytes of initialized data, and then BSS starts there, and then after that we've got the user stack, which we don't actually use at the moment. We just use the global stack. That really doesn't matter at the moment. Okay, and then the rest is bits of code, .text, bits, green lead val is an uninitialized bit of data. Okay, so that will be at that particular address. So if we were watching this through GDB, we'd be able to look at these things. And we've got all of our labels here. And that's a fairly small piece of program, although in fact it's larger than it ought to be because it's got bits of code in there that I'm reasonably sure shouldn't be there. And of course we can look and use size to find out how big the program is, and this will allow us to figure out if the code is going to fit and work. Okay, well, I think that's enough for today, and in the next seminars we'll probably look at things like particularly interrupts, and also looking at library code, because they're the two worksheets coming up that you really need to get done in order to pass this module. Okay, thank you very much and goodbye.